Hello again. Today we're talking or giving an introduction to routing. So when we want to connect multiple networks together, like on the screen here, we've got a network over here, 192.168.10. Actually, 0/24, that's the network number. That's a whole network in there. There's another network in there, 10.000/30. And the new network for our design on the right here, 172.20.00/16 is the network numbers. And we've broken up our network here because we've got a WAN link, so we've got a site over here, and this could be in a town somewhere in the world, and this is in another town somewhere else potentially, or at least across the city or whatever it is. Not too fussy, but we've broken up our network. Now the whole internet is broken up networks. It's actually chopped up into big networks, small networks, tiny networks, you name it, it's in there. And we need routers to actually connect them together. Your home ADSL or cable modem or whatever you're running at home is running a router. And it connects to your ISP and off you go. Now most of the protocols we're going to play with later are interior routing protocols. So inside your organization, this is potentially a site that you've got, so this could be head office in the green color there, and the orange side could be a branch office or a international office or something like that. And we buy a WAN link from our ISP, connect it through, and we control all the access that we've got there. But we've got different IP schemes across this network. So we need to configure it and get it up and running. And we're not going to use dynamic routing protocols at the moment. We're going to use static routes, or routes. You can call them routes if you like. I like the idea of calling them routes. I don't know why. I might start calling them routes. How about that? Okay. So let's have a look at what these routers actually routers. What these are. I'm probably not going to change. Let's call these routers. So what these routers are actually going to know at the moment is in their routing table, and actually have it up already. If you show IP, get it up there, show IP route, then this is what comes up. Now we've already built this routing table inside this router by actually configuring the interfaces. So if you look at that, that's the interface serial 000 over there, and it has the IP address put onto it of 10.0.0.2, and it's actually got a /30 or 30 bits in the subnet mask, and that's that interface there. The one below it is the 172.20.00/16 address network, and this is the absolute address there, and all well and good. Now the other cute one is a static address that I've actually already added. So a static address is something that we've actually typed in to say, let's find this network number, and we're going to send any packet that arrives that matches this destination 192.168.10. So we're only matching 24 bits there. We're not worried about the last octet there. Only worry about the first 3, and they have to match exactly. And if we do get a match, we're going to send that packet down serial 000. It's a bit like, I don't know, going into a kind of shopping center, or going into a maze or something like that, and at each doorway you've got someone, and you've got a ticket on you that says, I want to get to somewhere. And it goes, right, I'll have a look and see if the address matches, and if it matches that, well, yep, I'll send you out of that door. And when you get to the other side, you're going to see somebody else who will open a door for you, and that somebody else is this router over here on the left. They will then send you down a particular path and connect through. In our case, we've only got 2 routers, so there's only 2 doors, if you think of it like that. So there's a couple of things in here that we really need to think about. The way I've talked about it is we've actually got a match. So routers match these things. If there isn't a match in the destination of a packet, the destination field in a packet that matches 192.168.10, then this will drop everything because it says, well, I need to match the first 30 bits of a 10.0.0.0, and this one down here says I need to match the first 16 bits of a 172.20. So it does get a bit cute, the terminology. It doesn't have to be an identical match, and I'll show that a bit later, but here we have a 192.168.10.0/24. So let's put in another route just so we know how to do it. So configure terminal, conft for short, and IP route is the command. Now if I want to match 192.168 and I only want to match the first 16 bits, I can match the first 16 bits like that. This subnet mask here is not like a normal subnet mask we've put into our devices. It's actually in the router to say I only want to match 192 and 168. I don't care what other numbers exist in there. Even though there might not be a network in the universe that is just a 192.168, and there may be some, there probably is, but won't be many. But it doesn't matter as far as the router is concerned. It only needs to match so many bits. So let's have a look at that. So the basic command at the moment, IP route, the network number, or as many bits that we actually want to match, the mask to say how many bits, and then we actually need to send it out of a particular place. So I've just put a question mark in there and said, what options do I have? And pretty much most of this stuff down here is actually interfaces. So your Ethernet, your fast Ethernet, your gigabit Ethernet, a loopback address we haven't covered yet, but you can create them on your device and play with them if you like. Null seems weird because you're actually going to drop the packet. Null is the black hole, and anything that goes down there doesn't get out. Serial, we've got a serial interface up there, and VLAN information down there. We haven't covered VLANs yet, so we'll leave that one floating in the breeze as well. This one though is the next hop router. So I can put in the address of the next hop router, which is this address over here. And we would do that if our two routers are connected through a switch or switched network. In our case, we're actually going through a serial connection, so we don't need to put the next hop router's address. But if we do have a switch network and we want to make the whole thing run a little bit cleaner and more efficiently, then you put the next hop address in there. So I'm just going to put in serial 000 and chuck that in. And it does come up with this little line in there. And it says here, default route without gateway. So the gateway is putting in the next hop address there. If it's not a point-to-point interface, in our case it is, because that serial says whatever I send down the serial is actually going to come out at the other end. It's like a one-way road without any exits. As soon as you drive down it, you're only going to get to the other end. There's no way of turning off that interface or that connection. So if it is not a point-to-point, so if you're plugging a switch between the two routers, then there will be an impact performance if you just send it straight out of that interface. In our case, it's not. Now, the other thing we can put in there is the next hop address. So 10.0.0.1 is the address of this interface, and that's fine. It sits there, but let's go and have a look at our routing table and see what we do. So show IP route now has some interesting things going on with it. We've modified a few things here. So when a packet arrives at this router, it's going to look for the best match. So if I'm pinging 192.168.10.2, then I'm going to match the first 24 bits. So that route will be used. If I'm on this PC over here and I want to ping 192.168.9.1, then this router will look at it and look for the best match and says, well, I can match 192.168. I don't have to match anything else, and quite frankly I'm just going to send it down there as well. And the router's happy to do that. It does not care. It's not a connection-oriented protocol like TCP. It's connectionless, and whatever it does, it says, my job's done, poof, it's your problem over there. You solve it, because it's not my problem, I've done my job. Now the other one we have here is, it's not really written too well up here, but I'll just clean up my routes a tad. So I'll go into configure terminal again, and what I'm going to do is negate or take out this route that we just put in. So no IP route 192.168.255.255 out of our serial. And then I'm going to go back and look at my routing table. So if we show IP route again, then it comes up with this extra little bit thrown in, which is actually quite nice for us to know. It doesn't show it on this router, but anyway, that's okay. That thing there is a bit in Cisco called administrative distance, and it's the trustworthiness of this route that we've actually put into our system. How much does the router trust this route? You can see with directly connected, it doesn't have a 1 or a 2 or whatever. Its administrative distance is actually 0. This static doesn't have a 1 on it, and it's just that it's not actually written. Its administrative distance is still a 1, the same as this static route up here. So static routes have an administrative distance of 1, which is their trustworthiness. If we were to run, say, EIGRP as a routing protocol, its trustworthiness will be 90, so 90. So it's a lot higher than that. If we're running OSPF, it's 110, and if we're running RIP, it'll be 120. If we're running all three, then the lowest numbers will always win out as far as the final routing table is concerned. So that's good to know. So we can change this in static routes if you've got two paths to somewhere. So we won't cover that necessarily in this video, but we'll add some extra things a bit later. Okay, so let's just see what actually happens with all this. We've got a static route in there that's going to match 24 bits of this network from this network over here. So let's have a look at it, and we'll go into simulation mode, and I'm going to ping from 172.20. So let's ping 192.168.10 dot, and let's ping this address over here, 10.1. That should do it. And let's go into simulation mode. We've got to run ARP a bit. So it's been sitting there a bit quietly for a while. So it comes back and says, okay, I've got ARP sorted. I'm now going to run ICMP. So we'll see our ping go up to our router. Now what's the router going to do now? Let's have a look at our protocol data unit, which is our packet. We look at the inbound PDU details up here. So all I've done is double clicked on the envelope icon there, and it's come up and said, well, from the OSI model perspective, we're actually using layer 3. It does tell us here that the source IP address is 172.20.01 excuse me, and the destination IP address is 192.168.10.1. We can actually look at it a bit better in an IP header. So this is an IP header. If you haven't seen one before, there's ICMP sitting on top of it. So ICMP is a layer 4 protocol speaking to a layer 3 protocol speaking to the layer 2 protocol, which is Ethernet, and that's a frame there. But as far as our router is concerned, it's this little bit in there that's concerned about that. Destination IP of 192.168.10.1 is the destination that we want to get to. So it's going to go and look at its routing table and go, what's the best match that I have in my routing table? It's 192.168.10. I can match the 24 bits of that destination. I'm happy. Let's send it out of serial 000. There you go. So let's see what happens. Poof, off it goes down. It goes quite quickly, doesn't it? And it actually did get to this end. Now this end is not happy because it's got to run an ARP, so let's just quickly run ARP out of the way. And we've killed the first one, which normally happens because ARP takes too long for ICMP to sit there. So let's have a look at this thing go right through. Now we get again back to there, sends it on to our router. Our router has now found the MAC or layer 2 address of this PC, sends it to the PC. This PC says, okay, let me have a look at my outbound PDU. My destination IP address is 172.20.01. My source is 192.168.10.1. I need to send this to the gateway for it to solve our route for us or get to the other network. Just quietly, that's our default gateway, is doing that job for us. Now it's died up there, and let's have a look why. So we'll go into our CLI up there. Our access is prohibited, so we're going to type in Cisco and enable, and our enable password is class. Excuse me. So our user password, user access is Cisco, and our enable access is class. And on router 1, we're going to type in show IP route router. Now this router needs to look in its routing table and say, do I have a match for the destination packet? Now my destination packet says it is 172.20.01. That's the destination IP. Our router does not have a match for that, so it dies. It kills it. Throws it in the bin. We need to put another route onto this router because it only knows the two directly connected networks that it has. The shared connection, oops, between these two routers, 10.0.0.0/30, and the other connection that it's connected to is this one, which is 192.168.10.0. So, good. We need to put a route onto this router. Now I'm going to chuck another one in. So we've covered putting the actual network numbers in, and that's the best way if you only have a few network numbers. But there's another very important one that we need to know. So we're going to go to our config terminal. If we're connecting out to the internet, I don't want to type a million different static routes. I'm too lazy. So what I'm going to do is put in a particular route which you really need to know. Get out of there. So IP route, and I'm going to put that network number and that subnet mask. So the outcome of that is it will match every IP address on the planet, because it's all zeros. It says I'm not going to match anything. To some extent you could actually write into this, oops, 172 in there, but it still won't match anything because these won't be read, because the ANDing function will just kill them. So oops, I know what I'm doing. Very clunkily, isn't it? So IP route quad 0, so 4 zeros, with another quad 0, another 4 zeros for the subnet mask, is actually a particular type of route. So let's send this one down our serial interface. This serial on this side is also serial 000, the same as we've connected on there. And it gives us the same information. So let's just see in our simulation what's actually happened. So that should still fail. And then another ICMP comes in, which is the third ping, and it'll get right down to our PC and it'll come right back up to our router. And then this router is going to look at the, again, inbound PDU, the destination IP address 172.20.01, and it's now going to look at its routing table. So let's have a look at that, show IP route. And we've got this static in there. I'll come back to it because it's now got an extra little feature with that little asterisk, but it actually matches that. It's actually not matching anything, but because we've asked it not to match anything, it's matched. So let's keep going and see what happens. So it'll send it through and back to our PC. And then the fourth one goes through, and from a trivial exercise, we'll just click through that quickly. And we never got a response out of it. Let's go back and look at our PC, and it says here, request timed out. Now the request timed out because this router didn't send an error to this router because it received the dodgy packet from this PC. So I don't know if you remember seeing that red portion sending an error back there. So those two died. We froze time for a minute and put in the default route, and there it is. It's got two responses from 192.168.10.1. So at least two of our pings worked, and if we were to do it again, 4 of them would work because this routing is actually set up now. So let's go back to real-time mode and just have a look at our network here. So this static route that we put in is a particular type. That little asterisk says it's a candidate default there, and we've actually created this extra line in there, which is gateway of last resort is there to network there. So it's saying I've got a gateway of last resort. So if I do not have any of these entries matching anything, use this one as a last resort, and it's the final route that's actually looked at, and send stuff down that path there. Now that's good if you're connecting to the internet, because if you're right on the edge. But let's try something a bit interesting. Let me go back to my command prompt, and I'm not going to ping 10.1, I'm going to ping 9.1. And I'll go back into simulation mode. And if we remember in our routing up here, so from my PC, bring that up, oh, it's messy, isn't it? I want to ping 192.168.9.1, that IP address. So let's have a look at this router and see what actually is going to happen. Will 192.168.9.1 match 10.0.0.0 up to 30 bits? No. Let's have a look at the next entry. Will it match 172.20.0.0/16? No. Let's look at the next entry. 192.168.0.0/16. Yes, it'll match the first 16 bits, but there's another entry to look at. We want to get the most bits matching as we can. Will it match this one? Up to 24 bits, so will it match 192.168.10? No, it won't. So the closest match is actually this route, and that's the one it will use. Even though it's going to the same place and everything, it's not necessarily our problem. So what do you expect to happen? So let's, in our simulation mode, let's hit enter there and pop back. Now ARP has all been solved for everything, so we don't need to ARP everything. So let's go through the whole process. This outbound PDU says our destination network number 192.168.9.1 does not match 172.20.0.1 or 172.20.0.0, which is our network number, so let's send this packet to the gateway. Chuff it up to the gateway. This gateway says I'm going to match that route and send it to 10.0.0.1, which is the IP address on this side. And it goes there. So this one gets it and it says, you know, I don't have an absolute match for 192.168.9.1. I don't even have a match for 192.168. I don't have one, but I do have a gateway of last resort. I'm going to send it off to here. So let's do that. So it sends it back. What is this guy going to do? It's going to look at its routing table. Oh look, I've got a new packet come into my system. What can I match? I can match that one there. What is it going to do? I'm going to send it down that path. So you can see that it's actually, we'll go auto capture and just slow it down a bit. It's going to send it back and forth a whole bunch of times. What's going to stop it bouncing? This is actually a routing loop. It's not something we want. But what's going to stop it bouncing from router to router? Let's have a look at our packet. And we'll look at our inbound PDU details. And that little number there, TTL, time to live, is now on 121. You go, well that's interesting. Where does 121 come from? Keep that in the back of our minds. Let's capture forward once. Let's have a look at it now. Inbound PDU on the other routers now 120. Let's go again, another one. Have a look at our inbound PDU. It's now 119. What we're saying is every time this packet goes through a router, this value is decremented by 1. It actually started on 128. So it'll go through and bounce between these two routers 128 times before the router looks at the TTL at 0 and says, you've had a fair enough chance of getting from to your destination, from your source. Get nicked, you're out of here. Stop wasting my time. And that's it. It'll keep doing that, so we might speed this one up, for a whole bunch of times until it dies with the TTL. So routing loops do have a solution, but we still want to avoid them. And later on when we play with dynamic routing protocols, we want to avoid them, and they have their own methods in there. So this is going to take forever, this, isn't it? So we'll see how quickly it can run. Now there's one other type of route we can add into our system, and I'll just go through it. I'm going to get rid of that, that's starting to bore me. So we'll go back to real-time mode. Now right at the end of our static route, there's potential sometimes for us to have, actually, sorry, I'll just do this very quickly. It's going to get messy, I don't know if you remember all this. Let's add a new HWIC card, turn it on. Actually doesn't need to be turned on, but anyway, that's good. Actually that does. I'm going to cheat. Okay, you're still booting. I'm going to double cheat. And I'm not going to go there, I'm going to go serial 001, turn it on. Don't even need an IP address in there. What I'm going to do is put a serial connection. I'm actually not going to use that, I'm just going to use this guy now. And of course I messed it up. Well done, Rob. I'll take that one off and plug it into our serial 000. Maybe I didn't turn it, and go to there, turn that one on. Oops. Okay, so I'm not too sure what you've seen I've done. I've just created another path out of my network, and I'm just wondering if I haven't just stuffed that up, which I did. So potentially there's another path out of this network to get places. So let's put in a couple of routes on here. So I'm going to delete the static routes that I've put in, and I'm going to create that's what we want. I'm going to get rid of that one. I'm going to create a second route into our system. There it is, that's the one I want. Sorry, I've just been hitting the up arrow there just to see the previous commands that I've typed in. So if I show IP route now, I should have only directly connected networks. So directly connected the 10 network /30, the 11 network /30, and the 172.20 network /16. So I've cleaned up my static routes. So what I'm going to do is put on my gateway route out this way, but I'm going to have a backup path up that way, because if this link dies, I want to have a backup route out somewhere else. So remember the command IP route 1 2 3 4 1 2 3 4 zeros, so quad zeros. Now this one I'm going to send to 10.0.0.1 and leave it as standard, and the next one I'm actually going to send to 11.0.0.1. Hopefully that's correct actually. What did that IP address did I put in this one? Oh, I can't remember. Just put my mouse over 11.0.0.1, so I don't want to send it to 11.0.0.1, I want to send it to the next address up there too. And I'm going to put a little extension on it. So I put a question mark there, and this is the distance metric for this route. So it's going to not change the administrative distance. I don't think. Distance metric? I do. Let me put a 5 on that to say that's now not as good as that one. It's a backup. So if we show IP route, good. And this static shows up in our routing table. The other one will not show up because its distance, administrative distance metric, is now 5, which is not as trustworthy as this one, so only this one shows up. So there you go, static routing. So you can get quite complex with this if you build big networks and think about all the routes that actually need to go in. It does get relatively complex, and you really have to think quite clearly and slowly and make sure you get it right. And that's part of the deal for what we do as network admins people. We have to be able to think logically, clearly and slowly, and make sure that we're right when we're doing stuff. So if you do end up building a bigger network, put your routes in. You probably won't be using that quad 0 route unless you're right at the end of a network, but you know, it's not a bad way to go. All good. Hopefully you've learnt enough about static routing out of this to start playing around with it. Thank you very much.